My name is Maaneli Max Derakhshani. I am a postdoctoral researcher at Rutgers University in the Department of Mathematics. I am a theoretical physicist. My Ph.D. is in theoretical physics. And so I should mention this disclaimer that I am not a practicing climate scientist, but a physicist who's interested in climate science as an outsider somewhat, and from obviously a more realistic / skeptical point of view along the lines of Tom's point of view. Just wanted to put that out there in case anyone wants to take that into account when assessing my arguments. And I'm generally open to criticism and questioning of all kinds. So feel free to contact me if you have any thoughts of that sort. So I want to tell you about the possibility that ENSO is a dominant factor in global warming, as measured by satellite data and other temperature records. But I want to begin by explaining briefly what ENSO is, what the El Nino Southern Oscillation is exactly, because I think it is not entirely straightforward how it works and why it might be relevant to understanding global warming. So ENSO is an acronym that refers to El Nino / Southern Oscillation. Broadly speaking, this is a coupled ocean atmosphere phenomenon that occurs across the tropical Pacific Ocean. The phrase El Nino in Spanish apparently means Christ child, and it's apparently the name that Spanish fishermen gave a periodic warm ocean current around the tropics, which they observed usually to occur right after Christmas time. So I just have learned a bit about this through my own reading. I'm not an expert in the background history, but relatedly, the Southern Oscillation refers to changes in sea level air pressure patterns in the Southern Pacific Ocean between the island of Tahiti and also Darwin, Australia, both of which are located in the tropics. And the El Nino current is one part of this Southern Oscillation pattern. Here's a little globe diagram, which I got from the NOAA website, depicting the location of Tahiti and the location of Darwin on the globe. As you can see, they're both located in the tropics around the Pacific Ocean region. During the El Nino period, which is, as we all know, a warming period, what happens is that the average air pressure in Darwin, Australia, is higher than in Tahiti. And this turns out to cause changes in water surface temperatures in Central and East Pacific Ocean, which correspond to warmer water surface temperatures. And I will say a bit more later about why that exactly happens. Conversely, during the La Nina period, the average air pressure is lower in Darwin than in Tahiti, which causes cooler water surface temperatures. So the El Nino part refers to the warming episode of the El Nino Southern Oscillation, and La Nina refers to the cooling episode of El Nino Southern Oscillation. And the periods in between are often referred to as ENSO neutral periods. And El Ninos and La Ninas as episodes typically last around 9 to 12 months, sometimes a little bit longer or shorter. That's typically the time scale on which they persist. So to say a bit more about why these variations in air pressure between Darwin and Tahiti lead to cooling or warming, let's go back to the La Nina case. So there, the average air pressure in Darwin is lower than in Tahiti. What this implies is that the trade winds, which blow permanently from east to west across the tropical Pacific Ocean, get stronger than normal. The pressure difference, that is, between Darwin and Tahiti enhances the strength of those trade winds blowing from east to west. So the stronger winds end up pushing more surface water to the western half of the Pacific Basin, which means that a pool of warm water grows deeper and deeper in the western half of the Pacific Basin. And this ends up storing a lot of excess heat at depths in the ocean in that region. And what this does is it allows for colder, deeper water to rise to the surface in the eastern half of the Pacific Basin. So you have cooler water in that region. So this creates a large region along the equator where the ocean surface temperatures are below their normal surface temperatures, that is in between El Nino and La Nina periods, when the trade winds are just blowing at their normal strength. And as a result, over several months, heat from the atmosphere flows into the ocean because it's a cooler region of the planet than the atmosphere. And this results in heat being transferred from the atmosphere to this region of the ocean, and thus cooler air temperatures over that region, which end up being large enough actually to cool the global average temperature. So this is a satellite picture of the globe and the tropical Pacific Ocean. And this is a La Nina event occurring. The blue denotes the cooler regions. The bluer it is, the cooler it is. The orangish red denotes warmer regions of the oceans. This was apparently mapped out in 1988. So this is an instance of the La Nina event during that period, just as described. And on the other hand, during the El Nino event, when the average air pressure is higher in Darwin than in Tahiti, what this does is it causes trade winds to weaken or even reverse. And so what this does is it causes the amount of cold water that comes to the surface in the eastern Pacific Basin to decrease. So warm waters in the West Pacific Ocean slosh eastward, creating a large region along the equator where ocean temperatures are above normal. As a consequence, heat from the ocean then goes out into the atmosphere, which is a cooler body than that region of the ocean. And this leads to warmer air temperatures in the Pacific and thus warmer global average air temperature. So here is a corresponding image of the El Nino event in December 1997. Obviously very warm, as indicated by this metric, which depicts difference from the average temperature in this region, in this ocean region. So that in a nutshell is how the El Nino and the La Nina events occur. And a key point about the El Nino Southern Oscillation is that, at least on conventional understanding, it shuffles heat from the ocean to the atmosphere and vice versa. So the phases of the El Nino Southern Oscillation don't create or remove energy from the climate system, at least not directly. Arguably, the changes in the average air temperature would change the albedo of the planet, which could then change the energy budget of the climate system. But that would be a sort of indirect way of it doing so. At least directly, it seems to just transfer heat from the oceans to the atmosphere and vice versa, so that it's all the energy is internal to the system. That is the climate system. And for that reason, climate scientists generally refer to ENSO as a form of internal climate variability. But nonetheless, El Ninos do cause a global scale warming of the atmosphere, whereas La Ninas cause global scale cooling of the atmosphere, other things being equal. And the magnitudes of the warmings or the coolings are related to the strengths of the El Nino and La Nina events, respectively. Moreover, multi-decadal cycles happen where the tropical Pacific Basin takes physical states that favor El Ninos, say for 2 or 3 decades, alternating with multi-decadal periods favoring La Ninas. This is related to something called the Pacific Decadal Oscillation, which is another internal climate variable that's closely related to the ENSO phenomenon. So on this last point, here's a chart that I borrowed from a research report I'll be discussing later in the presentation, which illustrates how over multi-decadal periods, the El Nino Southern Oscillation varies between La Nina events. So this metric annual MEI, or annual multivariate ENSO index, is a common and widely used measure of the magnitude and frequency of El Ninos and La Ninas on a, well, in this case, annual basis. And this data set goes back to 1959 and ends in 2015. And as you can see, from 1959 to 1976, there were more La Nina events, that is cooling events, than there were El Nino events. And correspondingly, the cumulative version of MEI, which in this case is starting in 1959. 1959. It shows that if you sum up the El Nino and La Nina events in terms of their magnitudes, you find that there is a net decrease, which indicates more La Ninas and more intense La Ninas than El Ninos from 59 to 76. But on the other hand, going from 76 to 1998, there were significantly more El Ninos with, which were much more intense than the La Nina events. And thus we get this significant increase in the cumulative multivariate ENSO index. And then from 1998 to around 2015, there's only a very slight increase, slight inclining trend, if you do the cumulative measure. So this is an instance of how these multi-decadal cycles of ENSO can lead to global variations, that is global scale cooling and global scale warming events, and they're not necessarily equal. In this case, we see there's actually been, from 1959 to 2015, a net warming, so to speak. That is to say. And the reason I say I refer to it as a temperature change, that is a net cooling and net warming, is because the multivariate ENSO index, as we'll see in a second, actually does take into account temperature changes on the sea surface as well as in the air. It's part of the variables that go into computing the multivariate ENSO index, so that these changes refer to temperature changes as well. So here's another chart from the same report that shows, in terms of a bar chart that goes back actually to 1949, the multi-decadal cycles where, in this case, from 1949 to 1976, there were way more La Nina events and way more intense La Nina events than El Ninos. And then it switched in 1976-77. This is called the Pacific Shift. It's often referred to as a Pacific Shift, which led to much more global scale warming. And then this period was just very slight warming. And then again, the cumulative MEI confirms this pattern, this multi-decadal cycle. So this MEI, this multivariate ENSO index, is one of many measures of the frequency and magnitude of ENSO phases. Other measures exist, of course, like the Southern Oscillation Index, which we'll see also later on in the presentation, and also the Oceanic Nino Index. And they all show the same sort of pattern on multi-decadal cycles. As NOAA describes about the multivariate ENSO index, it is based on 6 main observed variables over the tropical Pacific, these being sea level pressure, zonal and meridional components of the surface winds, sea surface temperature, surface air temperature, and total cloudiness fraction of the sky. So the multivariate ENSO index at a given point in time is a linear function of 6 variables, all measured in the tropics, 2 of which refer to temperatures, sea surface and surface air temperature. And as we've seen, El Niños lead to warming of air temperatures globally, and La Niñas lead to cooling thereof. We've also seen that multi-decadal cycles of ENSO led to net cooling from 1949 to 1977, whereas significant net warming occurred from 1977 to 1998, and then not much of a trend one way or the other from 1999 to around early 2015, at least on the previous charts. So given these observations, it's natural to ask, how strongly do global average atmospheric temperature anomalies correlate with ENSO phases? Can ENSO possibly explain most of the warming and cooling periods in the temperature anomaly records? So this is the question I want to pursue now. And as a first pass, a first way of addressing that, I want to present to you this chart that I made, which convinced me to look into the question a lot further. So the top chart here is the University of Alabama at Huntsville's satellite temperature record, which measures the global average temperature anomaly of the lower troposphere of the Earth. And the record starts in 1979, and this is the latest chart. So with the latest data point in February of 2023. And each of these points is refers to a monthly temperature anomaly or deviation from a certain average depicted on the y-axis. And the red line here refers to the running centered 13-month average. Below is the multivariate ENSO index version 2, an updated version of the multivariate ENSO index, which starts in 1979 and ends in February 2023. So this is also the latest chart from NOAA. And something you can probably see right off the bat is that where there are spikes in the temperature, the global temperature anomaly in the satellite record, say here around 1998, also mid-2015, 2016, there were these big El Nino events. Correspondingly, where there were temperature declines, there have been La Nina events, like here as well, very slightly from here to here, from here to here. This corresponds to a La Nina event. And then there is this corresponds to this El Nino event. This area corresponds to this La Nina, and so on and so forth. This cooling corresponds to this period. Of course, as you go further back, you notice that around 1991, or 1990 to 1991, there was this cooling period and then a warming period. Whereas in around 1990 to basically 1995, there were all these El Niños, yet there was this dip in the temperature record. And even here, there was this huge, massive El Nino but not much warming here. And then this deep cooling period. So whereas we can see some clear visually see some clear correlations at certain parts of the record of the MEI and the temperature record, there are certain periods where they deviate. As it turns out, these periods correspond precisely to when major volcanic events occurred, which produced presumably ad hoc cooling of the planet through whatever aerosols were released by those volcanic events. And one other thing to notice is that there's actually a lag between the El Nino and La Nina events and then the spikes and dips in the temperature record. The lags are about 6 months or so. For example, here, this El Nino period starts in around 1997 and ends in around 1998. And this peak occurs in around mid-1998. Similarly here, this peak is in around early 2016, whereas this El Nino started in basically around middle 2015. And if you keep going through the record, you see that there are these lags of around 6 months. That is the spikes and the troughs that correlate with the El Ninos and La Ninas in this record are phase shifted by around 6 months or so. So as I say, you can see a clear correlation between monthly variations in ENSO from the MEI version 2 around 6 months prior to monthly variations in temperature, except for major volcanic eruptions occurring during El Ninos. In fact, the largest eruption events since 1979 that coincided with El Nino events, thereby temporarily negating some or all of the warming from them, were Mount St. Helens in May 1980, El Chicon in 1982, Mount Pinatubo in 1991, and Mount Hudson in 1991. And in fact, these two volcanoes can plausibly explain why there was this dip in this period from around 1991 to 1994 and 1995, despite there being all of these El Ninos. And the other eruption events occurred when there were La Ninas. So we wouldn't expect to see any loss of correlation. So that's just some visual evidence that one can gather offhand. But you might wonder, is there some more quantitative evidence, that is evidence quantifying these correlations in a more precise and systematic way? And it turns out there is a paper from 2009 by McLean and collaborators in the Journal of Geophysical Research, Influence of the Southern Oscillation on Tropospheric Temperature. And in this paper, the authors quantified the extent of correlations between monthly variance in the Southern Oscillation Index, which is another measure of the ENSO phenomenon, and monthly variance in both the UAH temperature record and the Rat Pack weather balloon temperature record. The Southern Oscillation Index, just to say briefly, is an index based on sea level pressure differences between Tahiti and Darwin, Australia, which, as we saw earlier, were relevant to determining whether El Ninos or La Ninas occur. And as NOAA says, in general, smooth time series of the SOI correspond very well with changes in ocean temperatures across the eastern tropical Pacific. So the SOI should be expected to correlate also with surface air temperatures and lower atmosphere temperatures. So the basic finding of McLean and collaborators can be summarized from this passage in their abstract. They say that the change in SOI accounts for 72% of the variance in the global tropospheric temperature anomalies for the 29-year-long MSU. MSU is microwave sounding unit, which is another named for a UAH satellite record. And it accounts for 68% of the variance in the global tropospheric temperature anomalies for the longer 50-year rat pack, that is, weather balloon record. Because El Nino Southern Oscillation is known to exercise a particularly strong influence in the tropics, we also compared the SOI with tropical temperature anomalies between 20 degrees south and 20 degrees north. The results showed that SOI accounts for 81% of the variance in tropospheric temperature anomalies in the tropics, which is what one would expect, given that the ENSO phenomenon originates in the tropics. And overall, the results suggest that the Southern Oscillation exercises a consistently dominant influence on average global temperature with a maximum effect in the tropics, except for periods when equatorial volcanism causes ad hoc cooling. That means global tropospheric temperature has for the last 50 years fallen and risen in close accord with the Southern Oscillation Index of 5 to 7 months earlier, thereby showing the potential of natural forcing mechanisms to account for most of the temperature variation. To visually see this, here is one of the final result charts from their paper showing the University of Alabama at Huntsville satellite temperature record, denoted by the gray line, also referred to as MSUGTTA on this y-axis. So this is the light gray line. And it's compared with this black line, which refers to the changes in the Southern Oscillation Index, but with a 7-month lag. This is a typo in their paper. They say this in a correction later, that this should just mean this should just say SOI, not SOI derivative. And so what you can see is that the two lines do correlate noticeably, or they overlap, they deviate somewhat. Where they deviate significantly, they note that these were volcanic events, major volcanic events like El Chicon and Pinatubo. But otherwise, there's fairly non-trivial overlap between the two, at least from 1980 to 1995, but also from 1995 to 2010, except for this period of a volcanic event. They otherwise correlate quite closely. And so this is around the 72% variation that was mentioned earlier in the abstract. That is 72% of the variance in the global tropospheric temperature anomalies as measured by the satellites can be accounted for by the 7-month lagged Southern Oscillation Index. And this is the same record for the weather balloon data, but going back to 1958 or so. And as you can see, the black line denoting Southern Oscillation Index correlates well, except for when there were these volcanic events, or expected. The question mark here indicates that a volcanic event occurred and presumably caused cooling here, but it's not entirely clear. But as you can see, the two lines do come back together after these volcanic events and correlate quite strongly with a 7-month lag once again. So that work by McLean et al. Seems to quantitatively confirm the qualitative visual observation that we saw earlier with the two charts that I showed initially compared to one another of the satellite temperature record and the multivariate ENSO index version 2. Now, what about ENSO impacts accounting for the long-term temperature trends? Because in the study by McLean and collaborators, they don't show that the long-term temperature trends of, say, the satellite record or the weather balloon record is accounted for by the ENSO phenomenon. They show that the monthly variations are accounted for by monthly variations in ENSO with a 7-month lag. But we would like to know if the long-term temperature trends in the satellite temperature record, let's say, can be accounted for by the net warming or cooling impacts of ENSO. So to this question, in a 2019 blog post entitled "Half of 21st Century Warming Due to El Nino," Dr. Roy Spencer, who's one of the co-analysts of the UAH satellite temperature record, along with Dr. John Christie, shows how the UAH tropospheric temperature trend and the Hadkrut-4 surface temperature trend each changed in the 21st century upon removing the big El Nino event in 2015-2016. And the reason he focuses on removing the big El Nino event is because of there's a net zero impact of El Ninos and La Ninas before that period. And the reason he focuses on the 21st century is to rebut a claim of some climate alarmists that claim that a certain infrared satellite is properly measuring global average temperature changes in the 21st century. So what Spencer notes is that if you remove the big El Nino event between 2015 and 2016, basically by restricting the time scale from the year 2000 to June 2015, as opposed to from 2000 to 2018, then the UAH trend, which for this period, 2000-2018, is plus 0.12 Celsius per decade, it drops to just 0.01 Celsius per decade. And the RSS trend, that is the other satellite record, halves from plus 0.2 Celsius per decade to plus 0.1 Celsius per decade. While Hadkrut-4 surface temperature trend drops from plus 0.16 Celsius per decade to plus 0.10 Celsius per decade over that same span. So in this simple analysis, Spencer shows that the cumulative impact of ENSO can have a substantial impact on those temperature records, accounting for a large chunk of it that's not a majority, to as much as half, or to as much as almost all of it, over 90% of the temperature trend, depending on which record is used. And so here are some charts from his blog post to illustrate this. The purple trend line refers to the UAH satellite with the plus 0.12 trend. And the green refers to Hadkrut with the plus 0.16 trend. And this is the 21st century multivariate ENSO index from 2000 to 2018, which Spencer shows has a positive trend, upward trend. So for this period, there was a slight net warming from the ENSO phenomenon. But when restricting the ENSO record to 2000 to 2015, there's no net trend. And correspondingly, the UAH satellite trend almost goes away completely, and the Hadkrut trend is cut down significantly. The CMIP5 here, this is the gray line, refers to the computer simulation models of the CMIP5 models that the IPCC relies upon, which I'm not going to go into much. But yeah, so Spencer shows that a simple analysis of this sort can significantly affect the global temperature changes. You don't need to appeal to any other natural climate phenomena or anthropogenic forcings. So Spencer's finding is suggestive that global warming trends in the lower troposphere are due almost entirely to overall warming impacts of ENSO, or at least significantly so. But then the question is, does this finding hold up over a more complete record, over the complete record of, say, the University of Alabama Huntsville temperature record, or even RSS? And what about the other temperature data sets like Hadkrut-4? Does it hold up over the complete record of those? So conveniently enough, there's a 2016 report by Wallace, Christie, and DeLeo titled On the Existence of a Tropical Hotspot and the Validity of EPA's CO2 Endangerment Finding, which addresses this very question. And this report is publicly available, and I encourage anyone interested to read it because it's very, very well done, extremely thorough. So the report does a standard econometric modeling of 13 different temperature time series, 9 of which are for the tropics, 1 of which is for the contiguous United States, and 3 of which are for the globe as a whole. And the authors ask, does adjusting a temperature time series only for the impact of ENSO via the multivariate ENSO index, the cumulative multivariate ENSO index, and a variable called the 1977 Pacific Shift MEI variable, account for all of the positive and statistically significant warming trend in that time series? And remarkably, in each of the 13 cases they analyze, their conclusion is yes. Just accounting for the impact of ENSO alone by these 3 measures of ENSO is sufficient to account for all of the warming trends in all 13 cases. And so here I want to show 2 striking examples that are also related to the examples that Spencer showed in his blog post. So first, I want to remind you of the difference between the cumulative MEI and the annual average MEI. The cumulative MEI results from summing the magnitudes of the El Niños and La Niña events, which leads to this net cooling from 1959 to 1976, and to a net warming from 76 to 98. And in terms of this bar chart, we see that the blue, which referred to La Nina events from, well, actually going back to 1949 to 1976, produced a net cooling, as you would expect, and as the cumulative MEI indicates, whereas from 76 to 98, we get a net warming corresponding to all these overwhelming El Nino events as compared to these few and small La Nina events. So one of the results I'm going to show you from the report is the global temperature of the lower troposphere satellite temperature anomalies. So they average the results of the University of Alabama at Huntsville data set with the RSS data set. And then they compare it to a multivariate ENSO index-based model fit. So the blue line refers to the global average temperature data set of the average of the 2 satellites data sets, RSS and UAH. As you can see, there's an upward trend from 1979 to 2015. And the red line denotes the global average temperature MEI model fit. So the model fits the trend extremely well. Now, doing their multivariate regression analysis and adjusting for the multivariate ENSO index change over this time period, the blue trend line that is referring to the temperature anomaly trend for the average of RSS and UAH becomes this flat blue trend line. That is a blue trend line with no net trend upward or downward. So just adjusting for changes in MEI completely flattens the warming trend that we get from the average of the 2 satellite data sets over this period of 1979 to 2015. They also analyzed the Hadley-Hadcroot for global average surface temperature anomaly data sets. And once again, the Hadley data set is the blue line showing a temperature increase from 1959 to 2015. And their MEI-based model fit is the red line, which fits the blue line trend extremely well. And once again, when adjusting for changes in the MEI, as described earlier, that takes the blue upward trend line, the positive upward trend line, which is statistically significant, to this statistically non-significant flat trend line. No net warming from 1959 to 2015 whatsoever, just by adjusting for changes in MEI. So, to wrap up, I've presented 4 lines of evidence strongly suggesting that ENSO is indeed the dominant proximate driver of global warming trends in the atmosphere. And I say proximate because ENSO is also significantly influenced by other natural climate phenomena, such as the Pacific Decadal Oscillation that I briefly mentioned before. Also planetary albedo. For example, the fraction of cloudiness right in the atmosphere, the fraction of clouds in the atmosphere. Also solar activity, such as sunspot cycles, and presumably underwater volcanoes and their activity, which is not well understood. In fact, it's still not well understood what causes the Pacific Decadal Oscillation or how exactly the other climate variables influence ENSO variations on a monthly basis or an annual basis or a multi-decadal basis. And as a consequence of these things not being well understood, ENSO variations are highly unpredictable. They're highly chaotic, highly unpredictable internal climate variable phenomena. So much more research is needed to understand the phenomenon of ENSO, how they're related to other natural climate phenomena. And in my view, if we really want to understand global warming much more deeply than we do right now, we should spend much more time understanding ENSO and the natural climate variables that affect it, rather than focusing so much on anthropogenic warming via greenhouse gases and the like. So with that, I will end the presentation, and thanks for taking the time to listen.
That was very interesting. On your last slide, you answered 2 of my 3 questions. We don't really know what causes them, and we can't really predict what's going to happen between now and 2050. My major question is, though, the Fortran climate models or Gavin Schmidt's climate models, do you think he has anything in there at all for these oscillations, or is it just the CO2 is the climate control knob, and that's why the Earth has warmed since 1975?
He might. I don't know the details of their climate models. It's possible that he does have some type of model for the El Nino Southern Oscillation. But the question is he taking into account the cumulative impact of El Ninos via, say, the MEI, or is he just looking at the MEI annual average and factoring that in to account for variations in the temperature record? In the model of Wallace, Christie, and DeLeo, they use MEI as well as cumulative MEI in this 1977 Pacific shift variable to model the impact of ENSO on the temperature record, because the MEI accounts for the annual, monthly, and the annual variations in the temperature record, but the cumulative MEI accounts for the multi-decadal variations in the temperature record. You need to incorporate different variables reflecting different timescales of the El Nino Southern Oscillation, at least to get the kinds of results that these guys get, where these temperature trends become flattened when you adjust for them. The other thing is, another difference to point out is that guys like Gavin Schmidt and others are using these computer models of the climate system, which are cartoonish caricatures of the actual climate system, and certainly don't take into account realistically the details of how ENSO occurs or how it's related to other natural climate phenomena. Whereas here, these guys are doing standard econometric modeling, which already takes into account from empirical data nonlinear relationships between different climate variables. So what these guys are doing is also scientifically very different from what people like Gavin Schmidt and other climate modelers are doing in their sort of work. Yeah, I would say that what's surprising to me is that I have not seen any attempt to rebut the findings of Christie and Wallace and DeLeo, despite this extensive research report being out there since 2016. And to me, that says something.
Do you happen to know if anybody has plans to heavily study this in terms of what causes it? Or are there papers already out there speculating what has caused it? Anything like that?
To the best of my knowledge, Roy Spencer has some papers where he's suggested that the Pacific Decadal Oscillation accounts for global warming and between the mid 20th century and the 21st century. These papers are around 10 years old or so. That's the most that I know of. I'm not an expert in the literature, so it's very possible people have looked at these things more closely, but I'm just not aware.
Any other points you'd like to make before we go ahead and wrap up?
No, maybe just one quick comment that people should not be afraid to acknowledge what their eyes are telling them when they see evidence that is more compelling than, say, the explanation of anthropogenic forcing. Whether in this presentation or in other presentations people have given, they should not be afraid to examine that evidence closely and follow the evidence wherever it leads, and not be cowed into believing anthropogenic forcing is the only way. But I'm sure your audience is already knows that. So
thank you very much. I appreciate it, and I hope to have you on again. Talk to you next time.
Thanks.